Hello Year 12 Further Mathematicians. Just going to continue with Chapter 2 in the Core Pure 1 book, 2.2 Modulus and Argument. These are two properties that we get from the Argand diagram that we studied last time, which is a diagram used to display complex numbers as two-dimensional numbers, a little bit like a vector from what we've done before. So the main objective today is to be able to find the modulus and argument of any complex number. The first thing I'm going to do is define what the word modulus and argument mean in this context. So the modulus of a complex number is, thinking back to vectors, it's like the magnitude of the complex number or the length of the complex number. So modulus is the magnitude of the complex number and the argument, again thinking back as to vectors and last lesson, the argument is the angle made with the positive real axis. Angle made with the positive real axis. So let's see what this means actually geometrically speaking. So imagine now you've got your Argand diagram or your complex plane, whichever way you want to describe it. It's got the real axis is effectively the x-axis and the imaginary axis is effectively the y-axis. You pick a random complex number, let's just say there, we'll call that Z1, actually let's just call it Z for now. We prefer to rewrite this as a vector, and let's label these two things in. So the modulus would be this length, and the shortest way to write modulus of a complex number is using this notation, absolute value, which we did previously as well. And then the argument is angle made with the positive real axis. And remember, angles going in this direction are positive. Anti-clockwise is a positive angle. So this is called the argument, which is abbreviated to arg z, argument of z. Now let's draw another complex number. Let's just pick one in this quadrant, call that w. Now for w we have, again, the modulus is the length or the magnitude, and the angle made with the positive real axis is called the argument, and you've got two options. You go in this direction, and that would be argument of w, or you could express it as a negative value and go clockwise instead. A few things that you might want to state, some formulas, but it is kind of stating the obvious. So if z is equal to x plus iy, then the modulus of z, the method used to work out the length of this complex number or the length of this vector, is Pythagoras' theorem. So it would be the square root of x squared plus y squared. And secondly, if I call theta the argument, So if theta is equal to the argument of z, then tan theta, it'll be connected to trigonometry, is always y over z. Tan theta is equal to y over z, which is effectively the imaginary part divided by the real part. And those two formulas will be you can easily derive them from the sketch, or you could just memorize them. Eventually you'll memorize them anyway because you would have done so many of them. But both of those formulas there are pretty key today. See what an example is going to look like. So imagine you have two complex numbers, z and w, and you have to find the modulus and argument of both of them. I would always encourage you to draw a sketch. I've never really seen anyone get one of these wrong if they have drawn a sketch, but I've seen plenty of people get these wrong if they haven't. So this complex number is 2 across 7 up. And that's Z. And the first thing you might want to do is make it look like a right-angled triangle. And it helps you then with these two formulas. So the modulus of Z, which would be the notation modulus of Z, is the square root of 2 squared plus 7 squared, which is root 53. And the argument of Z would be the angle made with the positive real axis, with this angle there, which I'll call theta. And if you think about it, without using this formula, you have opposite over adjacent, 7, 2, and that's why you pick tan theta is equal to 7 over 2. And then you make theta the subject. Obviously, your calculator should be in radian mode for this. The calculator should default into radian mode. They would have to explicitly say degrees in the question for you to switch to degree mode. So it's 1.29 radians. Don't really need a unit for radians. That would be it. Okay, now part B is the one people would likely get wrong if they didn't draw a sketch. So -4 -1 would be in this quadrant. Call that W. That is the right angle triangle, and let's work out the modulus first. Part B. Modulus of W is Pythagoras' theorem. Easy bit to remember. -4 squared plus -1 squared, which is equal to root 17. And this next part now, there's a few ways to do it, but like for example, you could treat this as a right angle triangle, work out this angle there, this acute angle, and then add 180 degrees to it, and that would give you the argument. The alternative is just to use this formula there, y over x, where y and x are the complex numbers, but then you do have to think about it afterwards. Okay, so let's see if I just use the formula. So if I said tan, let's use a different letter. Let's use phi. Tan phi is equal to y over x. Now what was y for this complex number? -4 minus I. There we go. Y is -1. x is -4, which is effectively a quarter. So tan phi is equal to a quarter. Inverse tan of a quarter gives you 0.245 to 3SF. And this is where people get this wrong, because remember, tan, or every single trig ratio, and there's infinite amount of answers. This answer is in the wrong quadrant. This answer is actually predicting the complex number being in this first quadrant, which it clearly is not. So you have to check to see if this does make sense. The one above, coincidentally, was just the right one, but this one is predicting the wrong quadrant. And the property for tan is you have to add 180 degrees or pi radians to get the next solution. And if you add pi, you get into this correct quadrant, which is 3.39 to 3 significant figures. And that would be one of the arguments for W. Now, I haven't really laid this out very well, so just want to say that's phi is equal to this, rather than continuing, almost doing that like a year 7 would, just working from left to right. But yeah, that's pretty much it. Now, there's one annoying thing I have to define at the end, which, as I said, the argument or trig ratios repeat. So the arguments themselves would repeat every 360 degrees or 2 pi radians. So I could give alternative answers to the argument. But there's something called the principal argument, and that dictates answers to be between minus pi and plus pi. So there's the extra definition, which is something called the principal argument, is where the argument of Z satisfies the following. It would be greater than or equal to minus pi, less than or equal to plus pi. And the answer I've given above wouldn't actually be the principal argument. And that is bigger than pi. I'd have to go in the opposite direction and subtract 2 pi effectively from this. So that would be 3.3. Actually, bring that answer up. Subtract 2 pi. That would be the principal argument for this one. So, or negative 2.90. If you're going to find the principal argument. It's always a little bit harder when doing it in radians, but if you get really confused, work it out in degrees first and then switch back. Right, if you find page 21, exercise 2b, I would like you to try the evens in that exercise. And that'll be it.